Hi everybody, I'm Sam, and I work for That Game Company. Right up front, I want to give a special thanks to Dylan Faust, who is our company's UI lead. He helped me make these slides look really amazing, so thank you, Dylan. And we are hiring, so if this talk is interesting to you and you like the idea of working on a custom engine, working on cool technical challenges that affect millions of players worldwide, then please reach out to us. And we have some fine folks right here in the front if you'd like to do that after the talk. So today I'm going to talk about how we got over 10,000 players into the same level all at once. But first, I want to talk a little bit about what we do at That Game Company, or TGC for short. So at TGC, our priority is emotion and human connection. We believe games can be a medium for taking somebody on a journey, pun intended, where they'll experience happiness, sadness, awe, despair, loss, or even love in ways that can be more meaningful and impactful than other mediums. So we want to help people form genuine human connection through our games. And these principles inform every decision that we make, from design to engineering. We released Sky, Children of the Light, in 2019, and since then, it's garnered a following of millions of players. Across the world, it's been downloaded over 200 million times, and in many ways, Sky follows in the footsteps of Journey. It's about adventure, companionship, struggle, catharsis. But while Journey was about a temporary, transitory connection between you and another person, Sky is about developing lasting relationships with people all around the world through shared adventure, activities, and creativity. Sky is a live service game, so our team works really hard every day to create new content and stories and events for the players. And we developed Sky using our custom in-house engine. So Sky was originally developed as an iOS game, but we've since ported it to Android, Switch, PlayStation 4 and 5, and this year we'll be releasing our PC version. So we've done all of this with a pretty small, talented, and passionate team of engineers, and of course, designers and artists and everybody else. So sometime around 2021, our CEO and design director, Genova Chen, had an idea for an in-game event for Sky, a music concert. So he brought this idea to me during our weekly discussions, and he asked, would it be possible to interact with thousands of other players at the same time in the same space, like a real-life concert? Now, for context, the most amount of players on screen at once in a normal game of Sky is 8. We have to run on an extremely wide range of devices, including some pretty low-end Android phones, and to this day, we still support the iPhone 6. So on top of that, our server architecture at the time also supported a hard-coded maximum of 8 players. And the vision for the concert was to increase that player limit by over 3 orders of magnitude, from 8 to 10,000. So it seemed like an impossible task, and I thought the idea was crazy. Fast forward to December of 2022, we launched our virtual concert featuring the music artist Aurora. And this wasn't just a music event. It had a story, a progression, an emotional arc. The player would experience awe-inspiring moments, otherworldly scenes, despair and darkness, peace and acceptance, and finally, a cathartic celebration, basically a really big party. They would do all of this with up to 4,000 players in the same level, all able to interact with each other for the debut of the concert in December of 2022. And last August, we did a concert encore supporting over 10,000 players. And for this, we received a Guinness World Record for the most users in a concert-themed virtual event. And the concert also worked across the thousands of different devices that run Sky, including the low-end Android phones and the iPhone 6. And by the way, we were also releasing our PlayStation port at the time, so our team definitely stays pretty busy. So how did we do it? Well, it started with a question. What's important to this experience? What do we care about? Emotion, so our main design pillar. We wanted this to be an emotional experience for the players. The feeling of togetherness, having a shared experience with thousands of players at once. Could we achieve this without rendering all 10,000 players in full detail? Perhaps the other players could be abstracted in some way. We just needed the player to experience the presence of others in whatever form that took. Interactivity. So we wanted the players to be able to communicate with each other in some way so that it was clear that you were experiencing this concert with real humans as opposed to just having a clever simulation that's simulating players. And we also wanted some level of interaction with the music itself. Inclusivity. So we wanted the concert to work on all of the devices that Sky runs on and over a large range of different internet speeds. We didn't want to leave any players out. So this is a picture from a real-life concert where the audience was holding up their cell phones as lights. And something like this seemed doable. Each player could be assigned a fixed seat and be represented as a point of light in the stadium. So rendering and networking that seemed like something we could do. But would this be enough? Would it be a good experience for the player to be fixed in place and see the other players only as points of light? How would the interactivity element work? Would you perhaps change the color of your light or just blink it on and off? Maybe other kinds of effects that we could do. Well, a big part of Sky is about movement and expression. So if that was severely limited during the concert, it didn't seem like we'd be able to satisfy that feeling of togetherness and level of interactivity that we wanted. OK, I'm going to get a little bit more technical here. And it starts with fish. So in late 2021, we started working on a new update for Sky called Season of Abyss. And it added a diving ability to the game, which we hadn't done previously, and focused on underwater exploration. But one problem that we had with our underwater environments is that they just felt pretty empty. So designers could place down some animated sea creatures here and there, but we just couldn't do that many of them without it tanking performance on our lower-end devices. And the reason for this is that each of these creatures were based on hand-animated skeletons. So they had their own individual AI and collision detection, and we had to do all of the animation logic on the CPU. And this gets really expensive when you multiply it out over hundreds or thousands of on-screen meshes. So to solve this problem, we implemented a little fish school system. And the entire school of fish was treated as a single entity. And we're able to optimize their steering and flocking behavior this way by having a sort of like little loop that just controls that one entity. And to render and animate the fish, we utilized static mesh instancing. And we implemented some procedural animation inside the vertex shader to make the fish wiggle as it swims. So the fundamental idea is to just defer all of the animation work to the GPU by having the vertex shader modify each position of the source mesh based on one or more input values like time or speed. And for this wiggle effect, we picked the sine wave based on the position along the z-axis in object space, and then we rotate the vertex around the pivot point of the mesh. And this works great to create this effect, and the CPU isn't burdened with any of the animation work. It's all deferred to the GPU. So as far as the CPU is concerned, all we're dealing with is a static mesh. So there's a wonderful GDC talk on this approach, by the way, that was a few years ago by Matt Nava of Giant Squid. And he was talking about the development of Abzu. And I definitely recommend that you check this out if you're interested in more sort of procedural ideas that you can apply to vertex shaders. But Abzu did a lot more with this idea by layering many more effects on top. But we were happy with this basic effect, and it kept the shader pretty simple for the lower-end phones. So with this method, we're able to render a lot of fish, even on low-end hardware. So in this scene, we had around 4,000 of them. And instancing them through this static mesh instancing system works great. But we still need to be careful about the overall vertex count in the scene. So if each fish is only 500 vertices, say, then we're already pushing 2 million vertices through the GPU per frame just for the fish. And for some of the low-end hardware, that's really not acceptable, especially considering that each vertex has to compute its procedural animation separately. So to solve this, we added LOD support to our instancing system. And in conjunction with some very aggressive fish mesh LODs, that allowed us to reduce the previous scene from about 2 million vertices to around 80,000. So we were also able to draw all of the instances using only 4 draw calls, so 1 draw call for each LOD level. And then to simulate the fish, we implemented a steering algorithm that computes an acceleration force to push the fish towards its target position and then decelerate it nicely as it arrives. So here I'm just moving the mouse around and fish is following it. So as we were developing this feature, Genova and I, in our weekly discussions, started to have the idea that this feature and the planned concert for the end of the year could have something to do with one another. I mean, if we turned all of the players into fish, and then we figured out a way of sending that across the network, then that could be a pretty cool experience. But it wasn't quite as Sky as we might like, and it's unclear how it relates to a music concert that takes place in a stadium. Still, if we're able to render thousands of fish with this method, then why not other types of creatures that are found throughout the world of Sky? If the same principles that we use to animate fish could be applied to our sky mantas, our butterflies, birds, other creatures, we could simply use the new instancing system to render them instead of their skeletally animated counterparts. Of course, we might need some pretty sophisticated vertex shader work to make that happen. But one of our graphics engineers, Oliver Castaneda, took on the work of writing these vertex shaders for all of the different creature types that we wanted to support. And most of those vertex shaders ended up being much more complicated than the fish version that you saw. But yeah, he did a great job with that. And another reason that we needed the animation to be a little bit more sophisticated on these creatures is because the idea would be that the player would be controlling one of them. So when it's up close to the camera, you can't fudge things so much. It needs to look a little bit more realistic with some secondary motion and so on. So Genova and the design team did some brainstorming, and this is basically how the main idea of the concert was formed. So the player would start in the Colosseum as a candle or a point of light fixed to their seat, but then they would be transported by Aurora into other parts of the world. So they would be transformed into different creatures. So for example, as a fish, you would swim with thousands of other fish, but they would be real players. They wouldn't be simulated through the fish school system. They'd be actually transmitted over the network. As a butterfly, you could fly with thousands of other butterflies, and they might be your friends or they might be strangers, but they would all be real people. And each type of creature and emotion, or rather, each type of creature and environment would represent a different emotion or a different part of the story. It would all be set to Aurora's music, which is largely about nature, so it just seemed like the perfect fit. But I think it is worth taking a brief pause here, because I really want to emphasize the following point. It was around July of 2022 at this stage of development, and the concert was planned for December. We still had no idea if any of this would work. The rendering side was looking promising, but the networking side was in its very early stages. And we still had a ton of other challenges to work out. For example, replacing the player avatar with a creature and making sure that the controls felt good for every single creature type. We needed to build tools for the designers so that they could set their levels up properly. We needed to make sure that, for example, player spawn points were distributed well enough so that players didn't all spawn in one position. If you got 10,000 players all spawning in one position in the map, bad things will happen. And there were so many details that we had to account for, mostly by imagining how it would work, because there were so many aspects of the tech still in development that it's not exactly easy to organize, thousands of testers to help you out as you're iterating. So we really just had to use our imagination a lot. And the design team was basically working on faith that all of this would come together. But they had other things to worry about, like how do you make thousands of players feel like a good experience instead of just a visual mess? How big do you need to design the spaces to fit that many players? So even if we got everything working, would it be a good experience or would it just feel like chaos? And we really had no reference to work from either, because as far as we were aware, no other game had tried anything like this. So there was a lot of nervousness and uncertainty about the direction that we were going. And I think that everybody, to one degree or another, was skeptical that any of this would work out. I mean, after all, we're going from 8 players in a game to 3 orders of magnitude more than that, which it just sounds absurd. So how would we actually send all of this player data over the network? So in a normal game of Sky, players are separated into these game instances or rooms that support up to 8 players each. Now, sending data for thousands or even hundreds of thousands of concurrent users is something that we've been able to do for a while and that we were able to do before the concert because we've got a lot of players that play Sky. But the problem is much easier when these individual 8-player instances don't need to know about each other. The bandwidth requirements from the player's perspective are pretty modest because you don't need the data for the 7 other players that are in your game room. You only need the data, rather, for the 7 other players that are in your game room, and you don't need data about anybody else. So if we were to use the same network protocol and send the same amount of data per player, but for a room size of 10,000 instead of 8, the amount of outgoing data would just blow up. And players wouldn't be able to handle that much incoming bandwidth either. So it was pretty clear that we would have to build a new protocol that was separate from our normal network data. Now, one really cool piece of technology that we've developed at TGC is our custom analytics server. So we use this to collect data about player behavior to get an idea of how we can improve the game. So for example, seeing what percentage of players make it through the core loop, or how many players engage in social interaction, what types of interactions they're engaging in, and so on. And one of the data points that we also collect is player position. So this allows us to visualize what areas of the game that players are getting stuck at, or where players like to hang out. And it's a really nice tool to be able to visualize this data, especially for the designers when they're trying to refine their levels. So I had some discussions with the back-end team early on about ways that we might be able to utilize this data for the concert. So an early idea was to take all of the positional data that we were receiving and some of the other data that we might need and build a kind of streaming service that could broadcast all of this out efficiently. Similar to a streaming video service, but basically a player data streaming service. And one of our back-end engineers, Jeremy Simpson, and our game server engineer, Alexei Oberchev, built a prototype of this, and we actually used this during development as a way to get real player positions into the game. So this image represents one of the first experiments that I made in combining live player positions from our server with the instancing system. And in this case, we're rendering thousands of players as little glowing jellyfish in our home level. And this was really cool to see. But by doing things this way, we were limited in a couple of ways. So firstly, there's a lot of player data that we just don't have access to on the analytics server. So for example, when a player shouts or does a particular emote, we don't have that kind of fine-grained level of detail. And secondly, the frequency of this positional data sent to analytics is very low. So it's on the order of 1 data point every few seconds at best. And this is in contrast to the much higher frequency data that the game server receives as it's doing all of the sort of moment-to-moment player interactions. And the game server receives those updates at about 10 updates per second compared to 1 update every few seconds. So ultimately, we decided that instead of using the analytics server, we'd simply build a new system which was built into the game server process itself And we now call that festival tech. And it would have the ability to kind of peer in to all of those individual 8-player game rooms. And this would give us access to all of that high-frequency player data that was available on the game server. Now, a single one of our game server processes, which is written in C++, by the way, will handle about 256 of these rooms at once, so up to 2,048 players. And to get to 10,000, we could have the servers communicate with each other in a full mesh network and share data about all of their players with all of the other servers. And that way we could get to that 10,000 target. And we refer to this setup as a game server cluster. So our game server engineer, Alexei, started working on the clustering architecture. And then I focused my own efforts on figuring out how to make the data stream that we were sending over the network as efficient as possible. So what exactly do we need to send, after all? I figured that the minimum set of data that we needed to represent a creature being controlled by a player was just position and some input bits. Input could be used maybe for some basic player expressions, like a shout, and it could probably be represented with 1 bit, and maybe we would have a couple of other bits for something else. We weren't quite sure yet. Orientation could probably just be derived locally from changes in position, so maybe we wouldn't have to send that over the network. And if that thinking was correct, that we could represent players with only this data, then what we really needed to focus on was compressing the positions. Since out of the 100 bits represented in this diagram, position is 96 of them. So first, some quick math. So normally, the network data in Sky is transmitted at a rate of 10 hertz. A position is 3 floats, or 12 bytes. And we're targeting 10,000 players. So multiply that all together, 10 hertz times 12 bytes times 10,000 players, and we get 1.2 million bytes per second, or 9 megabits per second, to represent all of those player positions. But of course, we need to send this data out to each player connected to the server. So we need to multiply that out by 10,000 again, and we get 90 gigabits of outgoing data. That's going to get very expensive. And it's also a lot of bandwidth for the player to consume, because we're going to be supporting, again, we want to support a wide range of internet speeds. And many players just don't have connections that are good enough to be receiving 9 megabits per second of data all the time, which is basically equivalent to like a high-quality 1080p video stream. Also, did I mention it's very expensive? So some questions came to mind. Can we send the data at a frequency that's lower than 10 hertz? Perhaps we can interpolate between the previous and the current position to smooth things out. Could we reduce the number of bytes that each position uses? Maybe we can use half precision instead of full precision floating point numbers. Could we send maybe only differences in position? This way, positional updates could be kept very small, and perhaps we could send the occasional keyframe to kind of correct deviation. Could we delta compress things? So in other words, if nothing has changed since the last update, then we just don't send anything. So this potentially could work well in the Coliseum, where players are just fixed to their seats and not moving. But it probably wouldn't work very well for the songs, where players are flying around and able to control the creatures. So it doesn't really optimize for the worst case, but maybe it was an option. And how about variable frequency based on distance? So perhaps for the furthest players, we update them at a much lower frequency than the ones that are closer to us. This also doesn't optimize for the worst case, though, and I'll show a good example of that later in the talk that you might catch. But again, maybe it's an option. So let's look at that first question again. Can we send the data at a lower frequency? So this is a test using positional data that we're receiving at a rate of once per second. Now, if we could send this data at this rate, then we're reducing our network costs already by an order of magnitude. We're just 10x reducing it, so that's great. But of course, having positions jump around like this really isn't acceptable. So we need some kind of method of interpolating them. So there was like a very clear solution to how to interpolate the positions that was sort of staring me in the face for the longest time, but for some reason it just took me forever to figure out. So I started out by just trying, obviously like linear interpolation, which I knew wouldn't look good, but actually surprisingly, linear interpolation looked okay once you started staggering when that interpolation starts, because when you've got like just a mass of stuff that you're seeing, then it all sort of smooths itself out in a weird way. And then I tried techniques like taking the current position, the previous position, and the one previous to that, and like making a little Bezier curve out of it, and tweaking the weights and so on, and just tried a bunch of different things. Nothing really looked super convincing. But if you've been paying attention to the talk so far, then you might have already figured out what solution I used. There's a little clue earlier. Any guesses? Close, yeah. So basically, I used the same steering algorithm that we used for the fish system. So with steering, we treat the latest position, or rather not the latest position, but the sort of the one that we receive after the latest position. So we've got the current position that we receive, we've got the one previous to that, and we actually interpolate, or rather steer, towards that previous position. The reason we do that rather than steering towards the latest position is to account for network latency, so that if our packets aren't coming in on time, then we don't get a lot of sort of starting and stopping. This does introduce some inherent delay into the system. There's a few seconds of delay sometimes where a player will move, and it might be 2 or 3 seconds until you see them actually move on the other end. But for the type of experience that we were trying to create for the concert, this seemed acceptable. And then in addition to just this basic steering idea, I also added in extrapolation so that it would account for that network delay for specific types of movement that we were doing in the concert. But the basic idea is the same as what we used for the fish system. And you might also have realized that this won't give us an exact one-to-one reconstruction of the player's path, because you lose a lot of that high-frequency data. But on the whole, it looks really smooth and natural. So the second question now, can we reduce the number of bytes used by a position? Can we do this? Can we use a 16-bit floating point representation to cut our position size from 12 bytes to 6 bytes? So quick refresher on 16-bit floats, often referred to as half. We get 1 sign bit, 5 exponent bits, and 10 fraction bits. So it means that we get good precision when the values are small, but it gets exponentially worse as the values increase. So half floats are often used in shaders where precision is less important than saving memory bandwidth. And here's a few examples of what those precision limitations look like. So for those small values less than 1, we get a lot of precision, but it gets rapidly worse as we go into higher values. So if our value is 1024 or above, then the minimum interval that we can represent at that point is 1. So we actually just can't even represent fractional values at that point. So half floats are a really nice way to compress data compared to normal floats when the values are small, but they're really not a good fit for things like world positions, which can have large ranges and need consistent precision along that range. I mean, think about it. We only have 2 bytes, so only 65,536 possible values per component, which really isn't enough for representing world positions, especially in the large levels that we were going to be using for the concert. So does this mean that we're out of luck? Well, what if instead of storing absolute positions, we just store a vector pointing from our position to the position of the other player? So now we have small XYZ values for players that are close to us, and then at that point we get a lot of precision, and large XYZ values for players that are far away from us, where we get much lower precision. But this is actually great because in a 3D game, objects that are far away inherently don't need as much precision in screen space due to perspective projection. So when it's far away, it's smaller on the screen, and each pixel represents a larger interval in world space. So those large intervals that we get between values as they start to increase don't really matter so much. So here's a test showing the difference between the 32-bit and 16-bit positions. So the size of the green dot here indicates the proximity to the player. And these are our original uncompressed positions. And watch closely. These are our viewer-dependent compressed 16-bit positions. So did you notice the difference? Probably not much of one, right? It's basically imperceptible. So it's completely worth the savings that we get from cutting our positional data in half. OK, back to our list of questions. Well, it turns out that we actually didn't even need to address these last three, because solving the first two was good enough. We now have a 2 times reduction in data rate from the positional compression and a 10x reduction from reducing the data frequency. And in the end, in fact, we used an update rate of 1 update every 1.5 seconds instead of every 1 second, because visually, I actually don't notice that much difference. So we ended up with a 30x reduction in our data rate from our original calculation, from 9 megabits per second all the way to 0.3 megabits per second. And that's equivalent to the bandwidth that you would need to play back like a potato quality video. So we felt comfortable that we would be able to handle that. Now, there was still a problem with the compression approach for the positions that I hadn't thought about when I was working on this. And some of you might have already guessed what it is. And if you have guessed what it is, then please talk to one of our fine people over here after the talk, because we'd love to talk to you. But anyway, I'll get back to that. So it was around August of 2022. We had around 3 months left to deliver the build that would be used for the concert in December. So we'd gotten the networking and rendering figured out, representing players as creatures, but we really hadn't been focusing too much on the Coliseum itself, which is where you'd start and end the concert. So our original idea was to have players represented as fixed points of light, perhaps with a way to turn their light on and off or change its color. But this just seemed a little bit underwhelming compared to the creatures that we'd be transformed into during the songs. But our team had another insight. If we're able to render creatures through the instancing system, then why don't we try to design an abstracted version of our sky characters? So one that doesn't require intricate bone-based animation and can be animated procedurally in the same way that we're animating all of the other creatures. So it wouldn't have to look exactly like the player's avatar. It would just have to give the impression of one. So this is what we decided to do for the Coliseum. And the funny appearance of these abstracted avatars became a bit of a meme in the Sky community, but it works really well to communicate the sense that there's other humans there with you. And another huge bonus to this approach was that there was no longer a technical constraint that the players be fixed to their seats in the Coliseum. And that allowed for some pretty spectacular moments, like this one where the players all get spit out like confetti by a giant aurora in the sky. And this also allowed us to add some fun activities to the Coliseum itself that would take place before the concert. And we added some of these for our 10,000 player event, like this giant ball game where you're trying to push a ball into a goal, and there's kind of 2 teams made up of thousands of players each. And we also added a sort of a tug-of-war type game. Definitely gives a whole new meaning to massively multiplayer. So another important aspect to rendering these abstracted avatars is the detail system. So for the nearest players, we add in extra detail that would be too expensive to add to all of the players. So this includes a dynamic light that emits from the player model, an enhancement to the steering algorithm that does ray traced look-aheads to make sure that we don't sort of clip through geometry. Since the low-frequency network data that we're receiving plus steering doesn't give us, again, a perfect one-to-one reconstruction. So we have to do a little bit of cheating to create those sort of high-frequency changes. And one more crucial design and engineering decision that we made for the concert was to keep the players who are in your immediate 8-player game room instance full-resolution avatars. And this worked really nicely to allow friends to have their full, normal level of interaction with each other and allow them to experience the Coliseum sections of the concert together in that way, while viewing the rest of the audience as something more abstract. And if you think about it, it's really not that far from how we think about a concert in real life. After all, we know our friends well, but we don't necessarily know the individuals in the crowd. They're just kind of the crowd. But nevertheless, we also wanted to provide some level of interaction between normal avatars and their abstracted audience counterparts. So we introduced a heart emote, a wow emote, a cry emote, a small and large shout, and a glow stick that you could wave over your head. And this worked both through the normal player avatar system as well as through the festival tech system. And it worked great for the types of crowd interactions that we wanted to create. One more thing that we wanted to come across to the abstracted version of the avatar was some data about who this player was and some information about their appearance, like their cape color. And since this type of data doesn't change very frequently, we implemented a kind of a fixed data system that synchronizes this data for all of the 10,000 players in the arena at kind of a fixed data rate. And so this means that if a player updates their appearance, other players might not see it instantly. There might be a few seconds of delay before that update makes it across. But this worked fine for our purposes. And finally, along with this fixed data set, we send a player identifier. So this is used to look up your friends. So if there's somebody who's not in your immediate 8-player room, but they're nevertheless friends with you, then you'll actually see their name tag over the abstracted audience entity. So that allows you to see that this person is actually somebody that you know. It's not just an abstract random figure. So for the player state that we need for those 1.5-second updates, this is what we ended up with. So 48 bits per position, 7 bits for input, and 2 for additional state. And we also have 1 bit at the top here, which is our active bit. So it indicates whether or not that player is connected or not. So you might be wondering why the active bit is necessary. If the player isn't connected, then why don't we just send nothing? Well, ideally, what we'd like to do is encode our network stream as an array of these player states. But the problem in doing that is what happens when a player in the middle of the array disconnects. So let's say this guy goes away. Well, now the client has no way of knowing which array entry is associated with which player. And this is going to cause all sorts of problems with the interpolation, as well as with the player appearance. Have one player changing appearance, like we could have potentially thousands of players all changing appearance all at once because they've changed their position in the array. But we'd also like to avoid sending any kind of player ID with each player state, because even something like a 16-bit ID is going to add significantly to our bandwidth requirements. So remember, we need to send thousands of these things every 1.5 seconds. So using this active bit, we can encode our network packets like this. So there's a header at the top of each packet representing the starting index and the count of player states in that packet. And now if a player is inactive, we can simply write 0 for that active bit and not write anything else. So it's kind of a form of delta compression in a way. And the really nice thing about doing things this way is that now the player IDs become implicit from the position in the array inside that packet. So the client always knows which player state is associated with which player. So all of the steering still works nicely and everything. There is still one problem, though, which I mentioned earlier, and it is with the positional data. So as mentioned, we're encoding the data not as an absolute position, but as a vector relative to the player. So what happens when we actually go to encode this network stream on the game server side? Well, every player needs to know about the position of all 9,999 other players relative to them. So we end up with this giant O(n)² loop, which, as we all know as engineers, is not good. For a server with 10,000 players in it, we have to do this calculation, simple as it is, close to 100 million times. So again, it's a very simple calculation, but doing it this many times incurs a very real performance penalty. And again, that's because every player's network stream needs to be encoded separately. We can't just encode a single buffer and then copy that over to lots of players at once. So out of all of the other challenges to get this system working, and there were many, This one probably worried me the most. I wasn't confident that just throwing extra processing power at it or multi-threading it would be a viable solution. And even if it was, it means we'd have to use really powerful servers just to do this very simple operation. So maybe we would just eat the bandwidth cost and just send absolute positions as float 32 instead, and it would almost double the amount of data that we were using up, and the experience might degrade for some players, and our costs would be higher, but it might be a sacrifice that we had to make. But I think I'd gotten kind of stuck on the idea that positions need to be relative to each player who is receiving the data. But in fact, as long as the position is relative to another position that's in close proximity to the player, then the resulting precision is very similar. So I sort of came up with this kind of spatial buckets idea, where what we can do is divide the world up into a grid. And these grid squares are going to be kind of big. They could fit hundreds of players, or maybe even thousands inside one of the squares. And we treat the center of each grid square as a pivot point around which we compute the half float vectors for each player. So the end result is that we only have to compute the vectors once for every player inside a given square. So if you imagine that each of these player icons in this diagram represents 100 players, which would be a pretty typical scenario for the concert, then we've managed to reduce the number of unique network streams that we need to compute from 1,300 to only 4, one per grid square. So this was a huge optimization that allowed our computing resources to be much more modest. So I've talked now about the bread and butter of the festival tech system, which is the networking and rendering. And once we had these systems in place, the team was very excited. It felt like we'd actually be able to pull this off. But the networking and rendering alone weren't enough to deliver the experience that we wanted. So, for example, one of the biggest problems still to work out was where would the players sit? This is a top-down view of our Coliseum. There are 10,144 seats in total, which was our actual upper capacity. So how do we make sure that each player gets assigned a unique seat? So to solve this, we implemented a separate service for this on our back end, which we call the reservation system. And this was largely the work of our back-end engineer, Jeremy Simpson, with our lead gameplay engineer, Kyle Holdwick, doing most of the work on the client side to hook all of this up. And it kind of works like an online ticketing system. So the player requests a reservation, and the reservation system's job is to then find a server cluster with available seats and reserve that seat for the player. And it also handles players' requests to switch seats. If they're not happy with the one that they're automatically assigned, then they can run around in the Coliseum, find a better seat, and join. And if they decide that they want to join a seat and then somebody else wants the same seat at the same time, then the reservation system handles those conflicts. So this system worked not just on a single server cluster with 10,000 players on it, but across multiple clusters, each of which represented a separate instance of the Coliseum itself. And in fact, for the December 2022 event, we had over 1.7 million people concurrently all around the world join the concert for its 8 p.m. debut. So that's a lot of Coliseums. So we debuted the concert as planned on December 9th, 2022, and this was not an easy project by any stretch. We had numerous technical and design challenges, and especially challenges around testing, making sure that our backend would hold up, and we had many bumps along the road and many worries and anxieties on that debut night to make sure that we were not sure if things were going to hold up. And I've only really touched on a handful of those challenges here. The rest could easily fill another hour. But in the end, we pulled it off. And most importantly, the reaction from the players was incredibly heartwarming. We got comments from players who don't play Sky, but just tried it out, just for the concert, saying things like, "It's the coolest thing that I've ever experienced in a game." And we had lots of people saying that, which made us feel really good. And what really made it kind of a magical experience in the end, I think, was, it was partly the combination of just art, design, technology, all coming together to allow thousands of players to interact with each other in this profoundly emotional shared experience. And I think even more importantly than that, the crowd itself kind of became the star of the show in a lot of ways. And it made each replay of the concert a unique experience that you could enjoy with literally thousands of people. And I really couldn't be more proud of our team for pulling this off. The concert was truly a company-wide effort to make a success, but I want to specifically just call out a few of the engineers who implemented some of the critical systems that made it all work. So I've mentioned Oliver Castaneda, Alexei Oberchev, and Jeremy Simpson. I also want to mention Kyle Holdwick, and then Wes Hawkins, Dylan Faust, Peter Lee, and our entire backend team. I think the system is really a testament to how some of the most transformative tech doesn't have to be just like a single brilliant algorithm. It can be a confluence of pretty simple ideas that just are all kind of brought together in harmony. I don't think that any of the individual techniques that I or the other engineers came up with for this system were particularly groundbreaking, but it's just the combination of all of these things that really made it sing. Musical analogies, yay. So I'll end this talk with some videos of the concert itself. So for those of you who were there to experience it, I hope that this will let you relive some of those memories. And for those of you who weren't, I hope it gives you some insight into what a moving experience this turned out to be.
You have a home in my queendom. You have a home in my queendom. I was a moving thing before I was a human being. I was the ice before it melts. I was the tree before it fell. My dear, come near. Far away, would I run off the world someday? Nobody knows, nobody knows. I was dancing in the rain, I felt alive and I can't complain. No, take me home where I belong. I got no other place to go. Warrior, warrior.
Thank you.